Hello and welcome to the AI Academy. In this course, we are diving deep into the telecommunications and network security. We're going to explore two key areas: the management concepts and technology concepts. These are fundamental for anyone preparing for the CISSP exam. Let's start with management concepts. This section is all about how we plan, implement, and oversee security measures in network environments. These concepts ensure that our networks remain secure, available, and resilient. Here are the key topics we'll cover: the C.I.A. Triad, which is the foundation of security, which is about the confidentiality, integrity, and availability. If you understand this, you're already on your way to thinking like a security professional. Remote access management, focusing on how do we securely connect to networks from different locations. This is especially important in today's world of remote work. Intrusion detection and response, understanding how do we identify attacks in real time and take action. Intrusion detection systems, the different types of IDS and how they help us monitor threats. Computer incident response teams, CIRT, the team that jumps into action when security incidents occur. Network availability, ensuring that systems stay online and accessible even during attacks or failures. RAID and backup concepts, protecting data by redundancy and backup strategies. Managing single points of failure, identifying and eliminating weaknesses in network design. Network attacks and abuses, understanding common network threats like DDoS attacks, sniffing, and spoofing. And trusted network interpretation, TNI, a framework for evaluating network security. Now, let's move into technology concepts, where we get into the technical side of things. These are the building blocks of how networks operate and how we secure them. Protocols, the rules that govern how data moves across networks. The layered architecture concept, how networks are structured for security and efficiency. The OSI model, the 7 layers that define network communication. TCP/IP model, the real-world networking model that powers the Internet. Security-enhanced and security-focused protocols, secure versions of standard communication protocols. Firewall types and architectures, how firewalls protect networks from threats. Virtual private networks, VPNs, secure tunnels for encrypted remote access. VPN protocol standards and devices, the different technologies that make VPNs work. Data networking basics, the core principles behind how networks function. Data network types, the differences between LANs WAN and MAN. Common data network services, essential services like DNS and DHCP. Data networking technologies, the hardware and software that make networks run. LAN and WAN technologies, the differences between local and wide area networks. Remote access technologies, secure methods for remote work. Remote identification and authentication technologies, ensuring that only authorized users can access remote systems. Now, let's define what telecommunications and network security really means. This domain focuses on the structures, transmission methods, transport formats, and security measures that protect data as it moves across both private and public networks. At its core, this domain is about ensuring 3 things: confidentiality, which means only the right people should have access to the data. Think of it as protecting against unauthorized disclosure. Integrity is about that data should remain unchanged unless modified by an authorized user. The opposite of integrity is alteration, which could be accidental or malicious. And availability is that the data and network services should be accessible whenever they're needed. If a system is down, it could be due to an attack or a technical failure, but either way, availability has been compromised. One of the biggest concerns in network security is preventing and detecting misuse or abuse of systems. Any compromise to confidentiality, integrity, or availability can lead to serious consequences. As we go deeper into this lecture, we'll explore how these concepts apply in real-world network security and how security professionals design defenses to keep systems protected. Now, let's talk about management concepts in telecommunications and network security. When we talk about management in this domain, we're really talking about how we oversee and secure networks, communication systems, remote connections, and security infrastructure. One of the most important foundational principles in information security is something called the C.I.A. Triad. If you've been in cybersecurity for any length of time, you've probably heard about this. C.I.A. stands for confidentiality, integrity, and availability, and these three principles form the backbone of every security decision we make. Let's break each of them down. Confidentiality is all about making sure that information is only accessible to those who are authorized to see it. Think of it like this: if you send an email to your boss, you don't want just anyone in the company, or worse, an outsider, to intercept and read that email. That's a breach of confidentiality. Confidentiality breaches can happen in a lot of ways. Sometimes, it's intentional, like a disgruntled employee leaking company secrets. Other times, it's accidental, maybe someone misconfigures network permissions and suddenly, files that should be private are available to everyone. So, how do we protect confidentiality in telecommunications and network security? We use security measures like network security protocols. These are sets of rules that help keep data safe while it travels over networks. Network authentication services. These help verify that users are who they claim to be before they access the network. And data encryption services. Encryption ensures that even if someone intercepts data, they can't read it without the proper decryption key. A real-world example is that when you visit your bank's website, you see a little padlock in the address bar. That means the website is using SSL and TLS encryption to protect the confidentiality of your data while it's being transmitted over the internet. Integrity means that when data is sent from one place to another, it arrives exactly as it was sent, no alterations, no tampering, no accidental changes. Let's say you're making an online purchase. You enter your credit card information, and the payment system receives it. But what if, along the way, a hacker was able to modify the transaction, changing the amount or redirecting the payment to their own account? That's an integrity failure. Loss of integrity can happen in two major ways: intentional attacks, where someone deliberately alters information. For example, a hacker might deface a company's website, changing its content. Accidental changes. Sometimes data is modified unintentionally. Maybe an administrator mistakenly overwrites a file, or a system error corrupts a database. And to protect integrity, we rely on several key technologies and practices such as firewalls. These help control incoming and outgoing network traffic to prevent unauthorized access. Communication security management involves managing encryption, digital signatures, and secure protocols to maintain data integrity. Intrusion detection systems monitors network traffic for suspicious activity and alert administrators if an attack is detected. A real-world example is that when you send an email, many email providers use a technology called digital signatures to verify that the message hasn't been altered during transmission. If someone tries to modify the message, the recipient will be alerted that the integrity has been compromised. The availability means that systems, networks, and data should always be accessible when needed. Even if your data is private and untampered with, it's useless if you can't access it when you need to. One of the biggest threats to availability is a denial-of-service attack. In a DOS attack, hackers flood a system with so much traffic that it becomes overwhelmed and crashes the system, making it unavailable to legitimate users. But availability isn't just about stopping hackers. It's also about keeping networks running smoothly even when hardware fails or when unexpected issues arise. To ensure availability, we use fault tolerance and redundancy, having backup systems in place so that if one system fails, another one takes over. Regular backups and redundant disk systems ensures that critical data is never lost, even in case of hardware failure. Acceptable login and performance monitoring, making sure users can access systems quickly and efficiently, without unnecessary delays. Reliable and interoperable and security mechanisms. Security systems shouldn't slow down operations, they should work seamlessly with existing infrastructure. A real-world example, think about cloud storage services like Google Drive or Dropbox. Even if one of their data centers experiences a power outage, their systems are designed to failover to another data center so that users never lose access to their files. That's availability in action. One important thing to remember about the CIA triad is that these three principles often compete with each other. If you focus too much on confidentiality, you might make a system so locked down that even authorized users have trouble accessing it. If you prioritize availability at the expense of security, you might leave your network open to attack. If you overdo integrity measures, you might create unnecessary complexity, leading to performance slowdowns. That's why network security management is all about balance. We need to design systems that protect confidentiality, maintain integrity, and ensure availability, without making life difficult for users. Every network security strategy revolves around these three principles. Whether you're setting up firewalls, encrypting data, managing remote access, or responding to cyber threats, you're ultimately working to protect confidentiality, integrity, and availability. As we move forward, we'll start diving into specific security technologies and management techniques that help maintain these principles in a real-world telecommunications environment. Now, let's talk about Remote Access Security Management, or RASM for short. In today's world, remote work has become the norm, and businesses rely heavily on secure remote access to keep employees connected while protecting sensitive data. This means that security professionals must carefully manage, monitor, and secure remote connections to ensure that only authorized users can access critical systems, without exposing the organization to cyber threats. So, what exactly is Remote Access Security Management? The RASM refers to the policies, technologies, and security measures that ensure secure remote computing. Whether an employee is working from home, a cafe, or even another country, remote access security helps keep data safe and networks protected. There are several remote access technologies that security practitioners need to manage. Each comes with its own security risks and challenges. Let's go through them one by one. Dial-up, async, and remote internet connectivity. The dial-up is an older technology where users connect to the internet using a phone line and modem. Async connections refer to asynchronous serial connections, often used in older network setups. Remote internet connectivity allows users to access corporate networks over the public internet, making security a major concern. Even though dial-up and async connections are mostly outdated, some organizations, especially in government and legacy systems, still use them, so security professionals need to ensure encryption and access controls are in place. Digital Subscriber Line, XDSL. DSL, or Digital Subscriber Line, is a broadband connection that uses telephone lines to provide high-speed internet access. Unlike dial-up, DSL allows you to use the phone while being online. Security concerns with DSL include intercepted data due to unencrypted connections, insecure routers that can be exploited by hackers, and weak authentication mechanisms that allow unauthorized users to gain access. Organizations need to encrypt data and ensure strong authentication methods to secure DSL connections. Integrated Services Digital Network, ISDN, is another older technology that allows digital transmission of voice and data over telephone networks. It was popular before broadband became widespread. Security risks of ISDN include eavesdropping on digital transmissions, man-in-the-middle attacks, and weak authentication mechanisms. Since ISDN is rarely used today, security professionals should ensure it is phased out in favor of more secure modern technologies. Wireless computing, mobile, cellular, and PDAs. The wireless computing has exploded with the rise of mobile devices, cellular networks, and personal digital assistants, PDAs. Today, smartphones and tablets connect to corporate networks daily, creating security challenges such as unsecured public Wi-Fi, hackers can intercept data on open networks. Or device loss or theft, if a work phone or laptop is stolen, sensitive data may be exposed. Or weak authentication, users often rely on simple passwords that can be easily guessed. To secure wireless computing, use VPNs and encryption to protect data on public networks. Enforce strong authentication with multi-factor authentication, MFA. And implement mobile device management, MDM, to remotely wipe lost or stolen devices. Cable modems provide high-speed internet over cable TV networks. While convenient, they introduce security risks such as shared bandwidth. Unlike DSL, cable internet is often shared among multiple users in the same neighborhood, increasing the risk of data interception. And default credentials on routers. Many users don't change the default admin passwords on their cable modems, making them easy targets for hackers. To mitigate risks, users should change default passwords on routers and modems. Enable WPA3 encryption for Wi-Fi networks. And use a VPN when accessing corporate networks over cable internet. Let's now talk about securing enterprise and remote connectivity. As more employees work remotely, organizations must secure enterprise networks against unauthorized access. Here are some of the key strategies. Virtual private networks. The VPNs create encrypted tunnels between remote users and corporate networks, ensuring that data stays secure even when transmitted over public networks. Popular VPN security protocols are like IPsec. It provides strong encryption for network traffic. SSL and TLS VPNs. It secures the web-based VPNs that don't require additional software. And OpenVPN. It is a highly secure, open-source VPN protocol. VPNs are essential, but they aren't foolproof. If a hacker gains access to a user's VPN credentials, they can still infiltrate the network. That's why additional security measures like multi-factor authentication are crucial. Secure Sockets Layer, SSL, and Secure Shell, SSH2. The SSL and TLS encrypts web traffic, securing remote connections to web applications. And SSH2 provides secure remote login capabilities, encrypting commands and file transfers. Many remote workers connect to corporate servers via SSH, so restricting SSH access and using strong authentication are critical for security. Remote access authentication systems. Authentication is a huge part of remote access security. Organizations use various authentication systems to verify users before granting them network access. Some of the most common remote authentication systems include Radius, Remote Authentication Dial-in User Service. Radius is a centralized authentication system commonly used for Wi-Fi networks and VPNs. It works by verifying user credentials before granting access. Logging authentication attempts for security monitoring. Supporting multi-factor authentication. TCAX, Terminal Access Controller Access Control System. TCAX is another authentication protocol, similar to Radius, but more secure. It separates authentication, authorization, and accounting functions. Provides stronger encryption than Radius. Is often used in Cisco network devices. Remote node authentication protocols. In addition to authentication servers, we also have node-level authentication protocols, which secure individual connections. Two of the most common are Password Authentication Protocol, PAP. It is a simple authentication protocol where usernames and passwords are sent in plain text. Because it lacks encryption, it is not secure and is rarely used today. Challenge Handshake Authentication Protocol, CHAP, is much more secure than PAP because it uses encrypted challenge response authentication instead of plaintext passwords. It prevents replay attacks by regularly re-authenticating the user. For modern networks, PAP should be avoided, and CHAP or stronger authentication methods should be used. Beyond authentication, security teams must also manage justification and validation of remote computing systems, ensuring that only necessary systems allow remote access. Hardware and software distribution, controlling which devices and software are authorized for remote access. And user support and remote assistance, providing secure remote support without exposing systems to unnecessary risks. By managing these risks, security professionals can keep remote access safe and reliable, ensuring that employees stay productive while company data remains protected. Now, let's move on to intrusion detection and response, a critical part of network security. Imagine you have strong locks on your doors and a security system installed at home, but how do you know if someone is trying to break in? That's where intrusion detection systems come in. They act like network security alarms, constantly monitoring for suspicious activity and alerting security teams when something unusual happens. The key thing to remember here is that intrusion detection is not preventative. It doesn't stop an attack from happening. Instead, it detects intrusions after they occur, so security teams can respond quickly and minimize damage. Intrusion detection process. Intrusion detection and response involve two main tasks: creating and maintaining intrusion detection systems, IDS, to monitor networks and systems for suspicious activity, and establishing a computer incident response team, CIRT, to analyze alerts, investigate security incidents, and take appropriate action. Let's break these down. An intrusion detection system, IDS, is a security tool that monitors network traffic or system activity and alerts administrators when it detects something unusual. There are two main types of IDS, network-based IDS, NIDS. It monitors traffic on an entire network rather than focusing on individual devices. Typically placed at key points in the network, like near a firewall. Uses packet sniffing techniques to analyze network traffic in real time. For example, a NIDS might detect an unusual flood of traffic, signaling a denial of service attack in progress. Host-based IDS, HIDS, it is installed directly on a specific computer or server. It monitors system logs, application activity, and file integrity, and can detect local attacks that network-based IDS might miss. For example, a HIDS might detect a malicious user trying to modify system files on a company's database server. Both NIDS and HIDS have their strengths and weaknesses, so many organizations use a combination of both for better coverage. There are also two different approaches to how IDS detect intrusions. Knowledge-based IDS, which also known as signature-based IDS. It works like antivirus software. It has a database of known attack signatures and alerts security teams when it finds a match. It is highly accurate because it only detects previously known threats. The pros of knowledge-based IDS are that they have low false alarm rate since it only triggers on confirmed attack patterns, and a well-documented alerts that security teams can easily understand. And the cons are that it needs constant updates to stay effective against new threats, and cannot detect zero-day attacks or brand-new hacking techniques. For example, if a hacker launches a known SQL injection attack, a signature-based IDS will detect it because it recognizes the specific attack pattern. Second is behavior-based IDS, also known as anomaly-based IDS. It uses machine learning and statistical models to detect activity that is unusual or abnormal for the system, and does not rely on a database of known threats, so it can detect new, previously unseen attacks. The pros of the knowledge-based IDS are that it can detect zero-day attacks and new threats that a signature-based IDS might miss, and can dynamically adapt to different network environments. And the cons are that it has high false alarm rate since it flags anything unusual. It might mistake normal activity for an attack, and requires more tuning to reduce unnecessary alerts. Example: if an employee suddenly starts downloading gigabytes of sensitive data at 3 a.m., an anomaly-based IDS might flag it as a potential data breach, even if no specific attack signature is recognized. Let's talk about one of the most critical teams in cybersecurity, the Computer Incident Response Team, CIRT. When a security incident occurs, time is everything. A quick and well-organized response can mean the difference between a minor disruption and a full-scale data breach. That's where the CIRT comes in. Many organizations also use the term CIRT, Computer Emergency Response Team, but because CIRT is copyrighted, CIRT is the more commonly used term. Regardless of what they're called, their mission is the same: to respond to security incidents quickly and effectively. What does a CIRT do? The primary responsibility of a CIRT is incident response management, essentially, handling and containing security incidents to minimize damage and restore normal operations as quickly as possible. This involves several key functions such as coordinating incident notification and escalation. When an incident is detected, the CIRT is responsible for notifying the right people like security teams, IT staff, and management, and escalating the issue appropriately. For example, a minor phishing attempt might be handled internally, but a major data breach could involve law enforcement and external cybersecurity experts. Having a predefined escalation path ensures that the right decisions are made quickly and effectively. Next goal is to minimizing business disruptions and financial impact. The cyber incidents don't just affect IT, they can bring entire businesses to a halt. The CIRT's job is to mitigate risks by containing the threat before it spreads, minimize downtime by working with IT teams to restore affected systems, and reduce financial impact, including legal costs and damage to the company's reputation. For example, if a ransomware attack encrypts critical data, the CIRT must act fast to isolate affected systems, initiate backups, and prevent further spread, all while keeping business operations running as smoothly as possible. After containing an attack, the CIRT's next step is investigation. This involves identifying how the attack happened. Was it a phishing email? A misconfigured firewall? A zero-day exploit? Analyzing network logs to track the attacker's movements. Determining whether data was stolen or compromised. And working with IT teams to fix vulnerabilities so the same attack doesn't happen again. In some cases, this may also involve forensic analysis to collect evidence for legal or regulatory purposes. Beyond responding to incidents, CIRTs are also responsible for managing network logs and security data, as the security teams rely heavily on logs to understand what happened during an incident. The CIRT is in charge of collecting, storing, and analyzing log data from firewalls, intrusion detection systems, and other security tools. Reviewing logs for suspicious activity, for example, unauthorized login attempts or unexpected file transfers. And ensuring compliance with legal and regulatory requirements for log retention. For example, if an attacker gains access to a company's internal network, reviewing VPN logs, firewall records, and IDS alerts can help trace their actions and identify compromised systems. And other responsibility is about overseeing incident resolution and post-event reporting. Once an incident has been contained and resolved, the CIRT's work isn't done. They must also evaluate the effectiveness of the response. What worked? What could be improved? Create a post-incident report documenting the attack, response actions, and lessons learned. And make recommendations for improving security controls to prevent similar incidents in the future. Many organizations conduct post-incident reviews where they analyze what happened. How did it happen? How well did the team respond? What security measures need improvement? This process helps strengthen cybersecurity defenses over time. A strong computer incident response team, CIRT, is a critical part of any cybersecurity strategy. No matter how strong a company's security measures are, breaches will still happen, and when they do, a well-trained CIRT can limit the damage and restore systems quickly. With an effective incident response plan, organizations can stay ahead of cyber threats and respond swiftly when attacks occur. Now, we will be discussing about ensuring network availability, which is about the redundancy and fault tolerance. Imagine a world where your network never goes down, your data is never lost, and your applications run 24/7 days without interruption. Sounds great, right? Well, that's exactly what we try to achieve with network availability. Now, in the world of cybersecurity and IT operations, availability means making sure networks, servers, and storage systems remain accessible, even in the face of hardware failures, cyber attacks, or unexpected disruptions. It ties directly into the availability principle of the C.I.A. Triad, which ensures that information and systems are always ready for authorized users. So, how do we prevent downtime and keep systems running smoothly? It all comes down to redundancy and fault tolerance. One of the biggest risks to availability is hard drive failure. If a critical disk crashes, data loss and downtime can be catastrophic. That's where RAID, redundant array of independent disks, comes in. So, what is RAID? RAID is a technology that combines multiple hard drives to improve fault tolerance. If one drive fails, data remains available. Performance: some RAID levels speed up read/write operations. RAID can be implemented in two ways. Hardware RAID uses a dedicated RAID controller for better performance and reliability. And software RAID is managed by the operating system but can be slower. Types of RAID and how they work. RAID 0, it provides maximum speed, no redundancy. In this, data is striped across multiple drives to maximize performance. But it has no fault tolerance. If one drive fails, all data is lost. It is best for high-speed applications where data loss isn't critical, gaming, video editing. But not suitable for business focusing of data. Next is RAID 1. It provides mirroring for full redundancy. The data is duplicated onto another drive. If one drive fails, the other continues running with no data loss. It is best for mission-critical data storage where reliability is key. But the downside is that it requires double the storage space, making it expensive. Another one is RAID 5, it is best balance of performance and redundancy. The data is striped across multiple drives with parity information stored for recovery. If one drive fails, lost data can be rebuilt using the parity info. It is best for the business servers that need both speed and fault tolerance. And the downside is that it has slower write speeds due to parity calculations. RAID 6 provides extra redundancy for high availability. Like RAID 5, but with an extra parity block for protection against two simultaneous drive failures. Best for large enterprises that can't afford downtime. But the downside is that it requires more disks, making it costlier than RAID 5. And the RAID 10, it combines the speed of RAID 0 with the redundancy of RAID 1. In this, multiple drives are striped and mirrored simultaneously. It is best for high-performance databases and enterprise applications. But the downside is that it is expensive because it requires at least 4 disks. While RAID helps protect data, we also need strategies to prevent full system failures. This brings us to server redundancy and clustering. Think of redundant servers as a backup safety net. If one server goes down, another one immediately takes over, keeping everything running smoothly. Types of redundant servers are like hot standby, which provides instant failover. A backup server is running at all times. If the primary server fails, the backup takes over instantly. The transition is seamless, users don't even notice the switch. And is best for the banking, stock trading, and emergency response systems. Another one is warm standby with minimal downtime. A backup server is partially active, syncing data periodically. If the primary server fails, the backup needs a restart before taking over. A slight delay in recovery, but much cheaper than hot standby. It is best for businesses that need high availability but can tolerate short downtimes. And the third one is cold standby. It requires manual activation. A backup server is completely offline until it's needed. If the primary server fails, IT teams manually bring the backup online. It is best for disaster recovery plans where cost saving is a priority. And the downside is that the recovery time can be several hours. Let's now talk about the server clustering. Instead of having just one backup server, server clustering allows multiple servers to work together as a single unit. So, how does clustering work? Multiple servers are linked together and share workloads. If one server fails, others pick up the load automatically. And the system distributes a network traffic, ensuring smooth operation. The benefits of server clustering are that it provides high availability as there is no single point of failure. Also provides load balancing as it spreads workloads across multiple servers. And scalability as more servers can be added as demand grows. Real-world examples of clustering are Google's data centers and cloud computing platforms like AWS, Azure, and Google Cloud use clustering for massive scalability. In today's digital world, downtime can mean huge financial losses. Whether it's a bank processing transactions, a hospital running medical systems, or an e-commerce website handling orders, availability is crucial. By implementing RAID, redundancy, and clustering, organizations can guarantee that systems stay online, even in the face of disasters. Now, let's talk about backup concepts, because no matter how strong your security measures are, data loss is always a possibility. Whether it's a hardware failure, accidental deletion, a cyber attack, or even a natural disaster, every organization must have a solid backup strategy in place. Think about it this way. If your organization lost all its data right now, how quickly could you recover? Would you be able to restore everything and continue business as usual, or would you be scrambling to rebuild lost information? That's why backups are so important. Tape backup methods: full, incremental, and differential. There are three main backup methods that organizations use, and understanding these is critical for the CISSP exam. Let's go through each one and discuss its strengths and weaknesses. A full backup makes a complete copy of every file on the system every time it runs. It's the most thorough method, but it also requires the most time and storage space. The full backup ensures that all data is backed up in one place, making restoration fast and simple. But it takes a long time to run and requires a lot of storage. It is best for the organizations that need comprehensive backups and can afford long backup times. And the systems that don't change frequently. Second one is incremental backup. An incremental backup only backs up files that have changed since the last backup, whether that was a full backup or another incremental backup. For example, if you run a full backup on Sunday, then an incremental backup on Monday, it only saves the files that changed on Monday. On Tuesday, it backs up only Tuesday's changes, and so on. It is fast and storage efficient since it only backs up new or modified files. But restoring data takes longer because you need all previous incremental backups plus the last full backup. It is best for the organizations with limited storage capacity or large amounts of data. And systems where changes happen frequently but need to be saved efficiently. And the third one is differential backup. A differential backup is similar to an incremental backup but with one key difference: each differential backup saves all changes made since the last full backup. For example, if a full backup runs on Sunday, then Monday's differential backup saves Monday's changes. On Tuesday, instead of just backing up Tuesday's changes, it saves both Monday and Tuesday's changes. It provides faster restoration than incremental backups because you only need the last full backup and the latest differential backup. But takes up more storage than incremental backups because the data keeps growing throughout the week. It is best for the organizations that want a balance between backup speed and restore efficiency. And systems that change moderately but need faster recovery times than incremental backups allow. Once you choose a backup method, you need a place to store the data. Here are some of the most common backup storage formats used today. The tape backups, the traditional choice. Even though tape backups might seem outdated, they're still widely used in many enterprises. They're cost-effective, reliable, and have a long shelf life, making them ideal for long-term data storage. There are four most common types of backup tapes: digital audio tape, DAT, originally designed for audio storage, but repurposed for data backups. Quarter-inch cartridge, QIC, small and inexpensive, mostly used in home offices. 8mm tape, used in older helical scan drives, replaced by more advanced formats. And digital linear tape, DLT, a high-capacity, high-speed tape format that is still widely used today. The choice of tape depends on the trade-off between performance, capacity, and cost. Optical media, CD and DVD backups. CDs and DVDs are sometimes used for small-scale backups, especially for archiving data that doesn't change. Write once, read many, worm, CDs, ideal for legal documents and compliance records that must be stored permanently. Rewritable CDs, CDRW, used for short-term backups where data might change frequently. These formats are low-cost, but their capacity is too small for large-scale enterprise backups. External storage, zip drives, jazz drives, and removable disks. Before USB drives became mainstream, businesses used zip and jazz drives for portable backups. Zip drives held 100 megabytes to 750 megabytes of data, widely used for personal backups. Jazz drives held up to 2 gigabytes and were used for high-performance applications. Today, these formats have been replaced by USB drives, external hard drives, and cloud storage solutions. Tape arrays, RAID for tape backups. Just like RAID protects hard drives, tape arrays use multiple tapes to create fault-tolerant backups. It uses multiple tapes as a single array. Allows fast, multitasking backups with fault tolerance. And commonly used in large enterprises for high-speed backups. Hierarchical Storage Management, HSM. HSM is an advanced backup system that uses both tape and disk storage to provide continuous online backups. It automatically moves older data to cheaper tape storage. Provides real-time backups for critical data. And commonly used in massive data centers and cloud services. Common backup challenges and how to overcome them. The backups are essential, but they come with challenges. Let's go over some common backup problems and how to solve them. Slow backup speeds. Full backups take a long time, especially for large data sets. The solution is to schedule backups overnight or on weekends to minimize disruption. Limited storage space. As data grows over time, backups require more storage. The solution is to use incremental or differential backups instead of full backups every time. Data loss between backups. If a system crashes right before a scheduled backup, new data might be lost. The solution is to implement real-time backups or use cloud-based continuous data protection, CDP. The backup media failure. The tapes and disks can degrade over time, making old backups unreadable. The solution is to regularly test backup media and replace old tapes before they fail. At the end of the day, backup strategies are a critical part of cybersecurity. Even with the best security measures, data loss can and will happen. Having a solid backup plan ensures that organizations can recover quickly and keep operations running smoothly. With the right backup strategy, organizations can ensure that no matter what happens, their data is always safe. Now, let's talk about single points of failure, a critical concept in network security and availability. Imagine you're flying in an airplane with only one engine. If that engine fails, there's no backup, you're in trouble. Now, compare that to a plane with multiple engines. If one goes out, the others keep things running. That's the same concept we apply in network design. A single point of failure, SPOF, is any component in a system that, if it fails, will bring down the entire system. The goal of network security professionals is to identify and eliminate these weaknesses to ensure continuous uptime and fault tolerance. Let's go over some of the most common single points of failure and how to manage them. Cabling failures. A network is only as strong as its cabling infrastructure. If a cable fails and there's no backup, network traffic stops. Different types of cables have different failure risks, so let's look at them one by one. Coaxial cables. The coaxial cables were widely used in older Ethernet networks, where multiple devices were connected to the same segment of cable. The problem is that if one section of the cable failed, the entire network went down. Exceeding the recommended cable length also caused signal loss, leading to failures. The solution is that the coaxial cables have largely been replaced by more modern twisted pair and fiber optic cables. Twisted pair cables. The twisted pair cables come in two common types, Cat3 and Cat5. The main difference is how tightly the copper wires are wound. Tighter twists reduce interference and improve performance. And the biggest issue is the cable length. If you exceed the maximum supported length, the signal weakens, causing connectivity issues. The solution is to use high-quality cabling, ensure proper installation, and avoid exceeding distance limits. Fiber optic cables. The fiber optic cables are immune to electromagnetic interference, EMI, making them ideal for high-speed, long-distance communication. They can carry large amounts of data over several kilometers without significant signal loss. The downside is that the fiber optic cables are expensive to install and require specialized expertise to terminate properly. The solution is to use fiber optics for critical network backbones, ensure proper installation, and have backup connections in case of failure. The topology failures. The way a network is structured, its topology can either increase resilience or create vulnerabilities. Let's break down some common network topologies and their failure risks. The Ethernet networks. Modern Ethernet networks use twisted pair cables in a star-wired configuration, which helps reduce failure risks. However, older Ethernet setups used coaxial cables, which were prone to single points of failure. The solution is to use switches instead of hubs and ensure redundant cabling. Token ring networks. The token ring networks were designed to be more fault-tolerant than Ethernet. The problem is that if one network interface card (NIC) failed, it could bring down the entire ring unless fault tolerance was built in. The solution is to use monitoring tools to detect failing devices and replace them before they disrupt the network. FDDI networks. The FDDI, Fiber Distributed Data Interface, networks use two rings, a primary ring and a secondary backup ring. If the primary ring fails, traffic is automatically rerouted through the secondary ring. However, some implementations use both rings for performance, eliminating the redundancy. The solution is to always reserve one ring for failover rather than using both for load balancing. The leased lines, single points of failure in wide area networks. Many businesses rely on leased lines, such as T1 or ISDN connections, for external connectivity. The risk is that if the leased line goes down, the entire office loses internet access. The solution is to use multiple leased lines from different vendors to prevent a single provider failure from causing downtime. Frame relay. The frame relay networks use a public switched network to provide fault tolerance. If a segment in the frame relay cloud fails, traffic is automatically rerouted through other available paths. However, failure risks can still arise if an organization relies on a single vendor. The solution is to use multiple vendors for additional redundancy. Aside from cabling and network topologies, other devices and systems can also become single points of failure, such as firewalls, routers, and switches. If all network traffic passes through a single firewall, router, or switch, failure of that device will shut down the entire network. The solution is to deploy redundant firewalls, routers, and switches, using load balancing and failover mechanisms. Power failures. The blackouts, brownouts, power surges, and voltage spikes can damage network equipment and cause unexpected downtime. And the critical devices like servers, firewalls, and routers are especially vulnerable. The solution is to use uninterruptible power supplies to provide backup power and steady electricity. Install backup generators in data centers and network operations centers for long-term power outages. The key to ensuring network availability is redundancy. Any component that, if it fails, will bring down the entire system must be identified and eliminated. By building fault-tolerant networks, organizations can reduce downtime, improve resilience, and keep operations running smoothly. In this session, we covered management concepts in telecommunications and network security, focusing on strategies to maintain availability, protect data, and respond to security incidents effectively. We explored the C.I.A. Triad, the core principles of confidentiality, integrity, and availability. Remote access security management, how to secure remote connections using VPNs, authentication protocols, and encryption. Intrusion detection and response, the role of IDS, CIRT, and incident handling in detecting and mitigating cyber threats. Network availability and fault tolerance, RAID, redundant servers, clustering, and backup strategies to ensure continuous operations. Managing single points of failure, how to eliminate weak spots in network design, from cabling to power supply issues. This concludes the management concepts section of our lecture. What's next? In Part 2, we will shift our focus to technology concepts, where we'll explore network protocols, architectures, security mechanisms, and defense strategies. We'll dive into the technical side of network security and learn how to build strong, resilient, and secure networks. If you found this lecture helpful, don't forget to like, share, and subscribe so you never miss an update. See you in Part 2.